Let's continue our Latin square. So if you consider the previous design, when we have blocking, it's almost like you repeat the data twice. First time you look at the car, and then second time you look at the tire. Now if you have the Latin square, in this case where I said the positions, every position used it once, then you can consider this data being recycled one more time. So it's almost like you have a square. First time you look from the top to the bottom to see the contrast. Second time you're looking from the tire perspective. And the third time you're looking at the location. So here are the data. How many tires do we have? A, B, C, D, right? So I can just have tire A, B, C, D, and then 16 number, a line for the A, B, C, D. And I can align the data for car. So I can align the data for 1, 2, 3, 4 as 4 treatment. And I can align for the positions as position 1, 2, 3, 4. So basically, you can rearrange this data. Every time you rearrange the data, what I'm trying to say is this. Excel. Okay. Remember, originally I have the treatment 1, treatment, or I can have treatment W, X, Y, Z. And then I can have observation, whatever I consider observation. So I said I have tons of observation here, and then paste special value, and then let's use the percentage to make it look easier. So if I have the data set look like this, what do? You just say that, okay, I can calculate the 4 treatments, sum of square, right? Or I'm doing right now is saying that, but this 4 treatment, I can consider that, oh, it's due to the the location, position 1, 2, 3, and 4. And if I consider there are 4 positions, okay, I can arrange the data and then paste special, transpose. And then I just said that, can you evaluate the sum of square this time, one more time? And then I said, oh, but by the way, the data set here, this is from different brand, A, B, C, D. So you can rearrange them, A, B, C, D, and then redo it one more time. Okay? Now, technically speaking, 16 observation, now I'm basically regurgitate the data based on position, based on the brand, based on the car. 3 times already, right? Right? Reuse the data set 3 times. Can I use it one more time? Here. Totally, how many degrees of freedom do I have? 15. And so if I do it for brand, and so pretend that I'm only looking at a brand, that's 4 minus 1, is just 3 degrees of freedom, 4 minus 1. Okay? Hey, what happened here? Okay. And then I said I look at a different car as a block, use 3 degrees of freedom. And now I'm saying I'm using the positions. Okay? How many degrees of freedom I can use? 3. So do I still have anything left I can use?
6.
I still have 6. So technically I can run one more time. The only things you have to worry is every time you said, oh, I'm going to look at it this way, I'm going to look at it this way, I use another 3 degrees of freedom. Sooner or later, there's nothing left for the error term. And the other way to do it, I'm just going to show you it's called Graco, Latin square. Okay, and here is the typical Graco looks like. Okay, so you see, in the okay, let me use this one. It's easier to read. Okay, so see the A is what? B and D and C and A. So capital A, B, C, D is dominating the subdiagonal. Can you see that? And when you're using A happen in here, 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 here. Every location use it once and only once. So even out. Now look at alpha, beta, gamma. It's the same things. They're basically saying that, oh, I will have alpha here. I'll have alpha. So every time you kind of like just alternating the whole things one more time. And why they're doing this is based on the assumption, okay? There's no interactions, okay? And if there's no interactions, I can look at everything's kind of in an additive way. And what do I mean by that? Actually, here's a good point. We're going to talk about factor analysis by the end of this week. So let me give you my versions of what is interactions. Okay. Anybody who want to speculate what is interactions? I just wanted to have a new presentation. Anybody want to speculate what is the interaction? Do you think that for system engineering, we'll study everything's in an additive way? Car is car, tire is tire, and location is location, nothing interact. Or sooner or later, everything interact with everything else. Right? If there's no interaction, the world is too easy. You don't have job security, right? But at the same time, if everything's interact with everything else, then how to dissect that? That's the problem. And I would like you to visualize this right now, because this relates to why we're doing the regression and the other stuff. Let me just have 2 lines, okay? And let me just say that insert a shape. Okay. Send to the back. Okay, so let's just say that I have a something, an effect, insert text box. Okay. And let's say this is a card effect or whatever, something I care about. And this is at a low level, so I'll just call A low. Okay, it's hard to control this. This is A low. And then this is A high. And so this is about, say, some effects I'm interested in. A low, A high, and the performance look like it's increasing, right? So I know that whatever I change from A low to A high, my performance increased. Okay? And that will be good things. And of course, could be, decreasing. But here, suppose that I said that I have another effect or something I'm interested in, and this is another factor, okay? And what do you think? A and B, these two different things, are they interaction? There is there interaction or there's no interactions? First of all, A increase performance to A from low to A from low to high, performance increase. B from low to high, no matter at A low level or A high level, the performance go up too, right? So both are, if increase is good news, both are increasing, right? And of course, I can have another one, and this time I can go the other way around. I'm just making up all the story because the data will tell us this. What does this one tell you? A move from low to high will improve the performance only at what kind of conditions?
When B is low.
Huh? B is low, then there's an improvement. But A is high, there's no improvement. Agree? What if it looked like this? What does that one tell you? Even though this is a 2x2, but it will exhaust every possible logics you can think about. This low to high performance or the measurement increased for B, but A doesn't make any difference, right? So in reality, I can duplicate the plot and just not, rather than plotting this, I can plot the other way around. What I'm saying is I can make this is A, this is B, and still talking about the same story. Okay? And first of all, this is just saying that A change or B change, something about our measurement changed. Okay? But in this case, you can see that I can look at them log B at low level, what happened AL to AH. Log at B at high level, what happened to AL to AH. Log at low level, what happened from BL to BH, or log from high level, what will happen to BL to BH. Okay? And if the world looked like this, will be just like our Latin square. Look at everything's, hey, I look at the picture this time, this way, and then reshuffle everything's and look at them one more time. Can someone ask the questions for me here? When I evaluate, or when you do your homework, when you try to evaluate the blocking effect of the Anova, of the blocking effect, or the tire, the car effect, or the tire effect, doesn't matter which one you organize or to calculate first. Does it change anything if you evaluate a row first or column first? Will that change your sum of square? So the things we're trying to say here is that they are independent. And if they're independent computationally, you can evaluate them in the, without a sequence. So put that down on your cheat sheet, okay? Statistical independence. What is statistical independence? You will be asked those questions as many times. What is statistical independence? Statistical independence means that the joint probability Pxy, x and y, equal to Px times Py. And if it's equal to Px times Py, equal to Py times Px. The sequence doesn't matter. And what's the easiest example I can show you? I'm flipping a coin. The coin could be head, could be tail. The probability will be, probability of head, probability of tail. Could be 0.5, 0.5, could be 0.6, 0.4. And then I'm flipping a coin, and then I'm tossing a die. The die could be 1, 2, 3, 4, 5, 6. If uniform distributions, probability of 1, probability of 2. And then when I ask you, what is the probability of having a head? And then the die is 4. And you can say that is 1/2 times 1/6. Right? Does it matter which one you calculate first in the multiplication? There is no sequence dependency. So independence means that it's multiplication in computation of the probability. And in operation means that the sequence doesn't matter. So you can calculate the car effect and then the brain effect, or then here is brain effect, location effect. Everything can be separated. Okay? So computation is easy. Now let's talk about our picture here. Okay? Here I'm showing a bunch of things. There's no interactions. So now let me show you the interactions. This time, let me look at this. People look at this. Do you think there's interactions? Think. Is there interactions?
Yes.
Why there are interactions?
Because they're inversely related to each other.
Yeah.
As one goes up, the other goes down.
So, in the job interview, okay, the most sleazy politician-oriented diplomatic answer you can use when people give you a situation to analyze, your first sentence will be what? Well, it depends. And then, of course, people say, depends on what? It depends on manpower, depends on resources, depends on a lot of stuff. So that's a smart answer to start with. It depends. And so here, what we're saying is that, what's the effect of B from low to high? It depends. If A is low, then the B effect is what? Positive. And if A is high, the effect is negative. And let me give you another one. What if, okay? I'm saying is this. Let me do it this way. Okay? Is A effect and B effect independent or not independent?
So B is dependent on A if B is high, but it's not dependent on
So in other words, well, let me make it a little easier. Okay? A effect from low to high is always positive. But the rate of increasing depends on the B. If B at a low level, the improvement is tiny. But if B at a high level, it's not tiny. Agree? Okay? So the only reason I'm playing this is kind of brainstorming, because how many different possibilities you can come up with, as many as you want. Okay? And you can look at this and say, oh, is there interaction? There's no interactions. So now I'm turning it back. If there are interactions between two effects, means that they are not dependent. They are not independent. A mingle with B, causing a lot of troubles. So graphically, I already talked about dependence, independence based on multiplication, based on the sequence does not matter. But here I'm trying to ask you, graphically, how did you know two things are independent or not independent? Can someone summarize really, really sharp, just one phrase, and said, Simon, no big deal. Just look at this. That summarize what is independent. There's interaction or there's no interactions. Come on, try your best. Give me a shot. People want to hire the sharp people, can summarize really quick. Sharp. Be sharp. Summarize it. What did you see? What we just analyzed in general, you just one look, you will say that, okay, here is the gamma rule. If you see this, independent. If you don't see this, dependent. Interact.
There is no intersection.
Huh?
If there is no intersection, then it is.
Very good. Young man, what about you? Want to say the same thing?
Yeah, I was gonna say if there's some kind of like proportional relationship between the two where they.
I'll say it the opposite way. Okay? Parallel. Whenever you see parallel, I don't care is this kind of parallel or this kind of parallel, even this kind of parallel. As long as, okay, and then I can move this. Okay? Here is what? A is a negative from A low to A high. Okay? And at a B high or B low level, doesn't really matter. The minute you see parallel, you know that Yahoo, the world is simple. I can evaluate them without thinking about interactions. Okay? So I would like whatever the analysis to do, I would like to see a lot of parallel, because that will make my world easy. And then, of course, to give my Christmas bonus, I would like to have few interaction terms and say that here is the tricky part. You know, A is good or A is bad. Depends. Depends on, or B is good or B is bad. Depends on your A at high level or low level. Okay? Whenever you see crossing, whenever you see non-parallel, you know there are interactions. And we're going to move to this after we finish the parallel part. Okay? So, the job interview questions is, sure, you said, it depends. And then people will say, it depends on what? Then you should say that, well, show me your data. Let me look at high, A low, B high, B low to figure out if there is any parallel line or there is no parallel line. If there are parallel line, the world is easy. Your problem is not hard to solve. Your situation is easy. Whenever you see the non-parallel line, you start saying that it depends. Okay? Depends on what? Here is the part we need to solve. Okay? And to do this is our goal for factor analysis. Let's need to come back to solve the simple one. Okay? So in this case, I reorganize this 3 times, and then I find the Anova table. Okay? And here, when I look at this Anova table, the error term is the same, but then I know that the p-value here is saying what? Position is not important. It's not significant. Car is important. Different car is significant, and different brand is significant. This is the F test, right? Using the F statistics 3.6. That's not. That's just mechanics. So you have a spreadsheet, you can get it done. And actually, if you right-click on my the handout I give you, you will find the answer. Okay? How to do that. I think what is important here is to look at this, is the partition of the sum of square. People look at the partition of the sum of square. Which sum of square is the most greedy sum of square? Which one?
The error.
The error is the greedy sum of square? Why?
It's because it has the most degrees of freedom.
Well, yeah, but actually that's the opposite. That's the bad news. Well, usually we keep the error as the bad news. Is you want to use which one is few degrees of freedom? Only few shots, but shoot up tons of sum of square.
The car.
The car, right? Car taking a lot of sum of square. The brand is the second one. Okay, so even though we're doing a simple Latin square partition here, okay, if I ask you if you want to investigate something, okay, you have position block, position effect, you have car effect, you have brand effect. Which effect you think that maybe I can ignore? Or which effect I think I definitely want to study first? Priority-wise, which effect you think is more important?
If p-value is lesser than 0.05.
No, that's the statistical argument. That's basically trying to say it's beyond reasonable doubt. The truth, the whole truth, nothing but the truth, that kind of legal statement for here. What I'm saying is that accounting-wise, usually, okay, I want to keep the main effect, the large sum of square, the most greedy car effect I want to study, brain effect I want to study, position effect I probably will ignore. Okay? Next, okay? Here is the way I redo this, and you have this, okay? You can calculate the total sum of square, the car sum of square, brand sum of square, and the position sum of square. And before it was a big homework for everybody, but now since I give you the spreadsheet, it's no fun to just copy paste. But you can tell, it's right. When a car effect, all the car will be the same because we treat them as a subway station. When we treat, the brain is the one we treat, so they're all the same. And then if you rearrange your position as your position effect, position left front, left back, and then they are the same. So one way to double check in the exam is make sure that you're from the same subway station. They should be, no matter I'm looking at a subway station on position, or I'm looking at a subway station on car, or looking at a subway station on brain. Since we're from the same subway station, they should be the same value. If you see something different, even though you regurgitate this 3 times, that rule still follow. Okay. The next things you want is, this time I said calculate the sum of square. Draw them like the pie chart, because the pie chart gives you a pretty good visualization. Okay, and here 3 degrees of freedom chewed up almost half of the pie, right? That's a very, very greedy piece I want to keep. And the positions, well, the brand chewed up a lot of sum of square. That's a big piece to keep. The positions, okay, it's not very important, right? It's not significant. But also look at here, is that's 3 degrees of freedom. Does it do much? Not much. So later on, this is something you should have in mind, is that whenever you, here, to do the F test, everybody agree I need to have the numerator and the denominator, right? So sooner or later, okay, this is the Takeuchi's argument. If I don't have enough error term, I need to borrow some error term. Which one should I borrow from? Borrow from the one not so significant. So the purple, if it says that I don't have enough degrees of freedom for my error term, where can I get my error term? Who you gonna borrow from? From the significant one, or borrow from the not so significant one? Borrow from the not so significant one. Okay, yeah. If this in Word or in mathematical proof is hard to visualize, but graphically this is pretty easy to visualize. Okay, and next we can rewrite this in a regression fashion. So how to rewrite this in regression fashions is basically, do it this way. So you still have your, every time you can say that, oh, I have my card effect, or so you rearrange your 16 number in column. And here are the handouts I gave you 2 weeks ago. Okay, so Latin square. Okay, let me do it one by one. RCBD. Okay. Computationally, it's no different from what you'd already done before. Okay? And I'm just going to repeat this in the following fashions. Okay, so let me start from random block design. Okay. So in the random block design, you're still doing the same things. First, you need to have an intercept row, agree? I mean intercept column, agree? And then after that, okay, people pay attention here. I have 4 different tire. I have 4 different tire, but how come I only have 3 row of tire variable? But because I can call one of the tire as my baseline 0, 0. So if I use A tire, A will be 1. If I use B tire, B will be 1. If I use C tire, C will be 1. Okay? If I don't use A, B, C, I'm using D, D will be 0 or 0. Agree? Similarly, can I have the car 1? So if car 1, using car 1, 1, 1. Car is 1. Using car 2, 2 is 1. Using car 3, 3 is 1. And of course, if it's not car 1, car 2, car 3, it's car 4. 4 is or 0. So here is the basic tricks. Okay? 4 tire. How many column do I need to have? 3. Because I use up the 3 degrees of freedom. 4 car I have. I should use 3 dummy variable. And then now I rewrite the 16 observation as it is. So totally, how many columns do I have? 7 plus y. And then, of course, what you do is what? You copy this, paste, transpose. So far, so good? And then once you have the x transpose x, can you times x transpose x? Right? Matrix multiplication. And then when you have that, what will be the first number? Total number of observation, 16. This is just like what we did for the simple regression or the polynomial. Except this time we're saying that, hey, tire could be high, tire could be A, could be B, could be C, or could be not A, B, C. Then that will be my baseline D. Car could be 1, could be 2, could be 3, or none of them will be my 4. Okay? And then once you do that, you can have x transpose x inverse. Okay? And here I want you to pay attention here is that then you can see that there are value around car and there are value around brand. But did you see any things in between? It's all 0, 0, 0. Right? You follow me? Here are the car things within car. And what usually when you see this, okay, that means that your model doesn't have any interactions between brand or position. And why? Because we're doing Latin square, right? We never let low, low, high, high, or high, low, low, high happen. And then, of course, you can calculate x transpose y. And then when you put them together, okay, you can find your regression term. And once you find your regression term, intercept is 8.7. If it's car, if it's brand A, is 3.3, 1 point this, and here is your parameter. So now, if you said that, hey, here's my first observation, it's car 1. Brand tire is using A, and car is using number 1. So what will be my predictions? Okay, so all you have to do is this. Let me do this just for fun. Okay, I'm doing this multiplication between the parameter beta times x. You can just do this. Okay, first one, intercept is what? 8.7. Agree? Everybody see the intercept is 8.7 of the performance coming from? Okay, next I need to talk about my tire effect. Tire is what? What is my tire for first observation? A, right? So A, the effect of A is what? 3.3. Okay? And then do I need to think about B or C? No, if it's A, it's A. It's not going to be anything else. Okay? And then which car did I use? 1. And what is my car 1 effect? It's 4.3. The block of the car 1 effect. So if you have those three numbers, I got it wrong here. It's not 87, it's 8.7. Okay, so my prediction, okay, should be 16.3, and yeah, here is, I run it up. If you use this one, let me redo it, equal to this guy plus car A, brand A, and then effect this. I get my 16.189 or 1A. Let me increase it a little bit. Okay, so everybody see where this prediction coming from? Yeah? Yeah? So why I'm doing it this way? Because this is later on, we can code very, very complex situation just by doing this. So similarly, what will be this one? This one will be 8.7 plus what? Minus the C effect, negative 0.2. And so now you can get all your prediction value out, right? Agree? And then, of course, your error term will be what? Your observation minus your prediction. That will be your error term. So once you do that, what will be your sum of square error? Your sum of square error is all the error terms combined. Agree? And then, of course, I can calculate my tire effect, only tire times my part. And then I can calculate my brand effect, only the brand part. And so I can figure out my sum of square of my tire effect, sum of square my brand effect, and of course, what will be my model if I only have two things? My tire effect plus my brand effect, that will be my this one. So the total sum of square is equal to the variance times 15 because it's divided by 16. So here, people see what I did? I redo your homework last week rather than using the subway stations analogy. I'm just doing it in a regression way. Okay? And so you can cross-check the two. Okay? Why I'm doing this? So I can torture you? Because sooner or later, right? We're not just interested in are you high or are you low. We're interested in is what? Okay, so should I go straight forward? Should I turn right? Should I turn left? In order to what? To get better value. So in order to do that, I need to find those values. Okay? Now let me try another one. Now let me try the Latin square. Latin square is the blocking with some extra effect, right? So how will be that extra effect gonna look like? People, I have 3 columns for my tire. See that? I have my 3 columns for my car. See that? So now I have 3 columns for my positions. So they use that all the degrees of freedom. And then you can have your X transpose X to get your X transpose X matrix. And usually, this is the things I check is, hey, I have 16 observations, should be 16. So if the homework, I give you 25, what would be the first value there? 25, right? And can you calculate your X transpose X? Okay? And then can you calculate your X transpose Y, and then you get your beta value. Except this time, the total number of sum of square. Does it, young lady, the total sum of square, 80.94, gonna change because I'm doing blocking or doing Latin square or even doing Graco Latin square. 16 observations, that's it. You don't, your pizza or your big gulp of Coke, that's all you have. Our job is not, we cannot do anything about the total. The only thing we can do is what? Even the error term, okay? We just say that some of the error term now gonna be explained. Before we explain car, we explain tire. Now we still explain car, we still explain tire. On top of that, hey, some of the error term is not really error term, is my positions effect. So I have my positions effect. So here, I'm showing you how to do this using a regression fashion. Okay? And for all of you, by now, this is the time you have to ask yourself, can I see the world 2 different ways, even in the Latin square way? Because you can do it in the Latin square way. Later on, when we start having the interaction term, you can do it with even more complex things. Okay? And what's the difference between the regression view and the simple Anova view? Anova view, I'm just saying that, am I high or am I low? But the regression view, since I have the slope of each term, so now I can say that, hey, am I moving toward A or toward B or toward C is a good idea. Here, can you tell? If I want to use the tire, say this is a tire life, then A is a good life. C is a bad life, because using C, my life gonna get cut really quick. Tear and wear gonna be quick. Okay? And then on positions, position 1 is bad, because position 1 give me negative. Okay? But if this measurement is about wear and tear, then negative is good news. I want to minimize wear and tear. So the less, the better. Or the more, the better. But no matter what, I'm just recalculating your sum of square rather than using the high and low, subway station analogy. I'm using the regression approach. Okay? Please don't copy and paste. I heard that, actually I know that some of you did it. When I give you the 3rd order polynomial, and people just plug them into a 2nd order. And don't do that, because if you just plug and play and not thinking this through, you're not going to get it. And, it's dangerous that way. Okay? Yeah, I let you double check, right? If you don't get the same answer, you know something's wrong. Okay? And let me show you another one. Thanks. Okay. And this time, I'm doing the variable rather than using the 1, 1, 1. The baseline I'm using is called -1. Okay? And what's the difference between 0 and 1? And see, it's all -1 for baseline here. Okay? So there are two different ways to set up the variable. Okay? And one way to set up the variable is just, hey, 1 here, 1 here, 1 here. Here is, I will have a base block, it's called -1. And it doesn't mean much to you right now, but when we start doing response surface optimization, this means a lot. Here, if I consider I'm in the neutral positions right now, okay, and if I turn right, go right one step, it's called +1. Then if I step to the left, should be what? -1. If I go forward, it's +1. Then step backward will be -1. So the beauty of doing this is when you have a very, very complex response surface, consider this room, okay? This room, right in the middle there is 0, 0, 0. Okay? So every time you can have what? Going up for +1, or going to the ceiling is +1, or going down to the floor is -1. Going to the back door is, say, +1. Going to the door close to me is -1. Going to the right wall is +1. Going to the next wall is -1. So using this approach, I'm basically trying to show you that you already have this topology in mind, is that we're not just doing the regression. We're using the regression to figure out, so what? Who cares? Which way gonna give me the good answer? So you play with this, you still get all your parameter done. And when you get your parameter done, you get your prediction, you get your sum of square. Okay? But this time, you basically try to figure out is, okay, your composition and everything's just like before. So this answer is no different from your previous answer, except I'm just doing it using this kind of +1, -1 options. Why this is important? Because in the, I have a few minutes. System engineer. Do you think do nothing is an option?
Yeah.
How many of you think do nothing is not an option? When your boss said, what should we do? And people say, oh, we should use option A, we'll get more profit. We should use option B, we'll get, less cost. Can you always have a do nothing options? Yeah? So 0, 0 is do nothing options. Okay? So here, I know probably none of you will take my control class. Okay? When you develop a self-driving car, okay, can you only have accelerator? Do you need brakes? Do you need to have a backward gear? Okay? Can you have your steering wheel only can turn right? So you can think about your car. It's the same things. You need to have all the possible control. positive 1, negative 1 in order to do something. Here I'm just saying that, okay, we're moving the picture of 16 observation getting more and more complex. Originally, we're just saying that, hey, where are you live relative to a central mean? We call it a central station. Then we start saying that, well, we can treat those 16 observations kind of like there's a hidden line inside, and how to figure out that line. And then we start saying that, well, maybe there's not one line, there are several lines. Depends on you're talking about the slope change or the intercept jumped. And then finally we said that, well, if you can think about their slope, their intercept, you can put them into a bunch of, well, are we using A, are we using B, relative to a baseline. Now, it's 16 observation, but those 16 observations turn into a self-driving car. I have options now. My option is, should I use tire A, tire B, tire C? Should I use car 1, car 2, car 3? Should I use position 1, position 2, position 3? Okay? Which one is the, yes?
I just kind of had a high-level kind of question.
Yeah.
Is there a difference between interaction and correlation?
One by one, okay? Slowly, okay? Interaction, when I talk about two things are dependent or independent, those are the concept for interaction, right? How did I define it? Pxy equal to px times py, or exy equal to ex times ey. Expected value or probability? Which one did I use? Probability, right? Tossing a coin, flipping a coin, tossing a die. Okay, so probability is the interaction term. Okay, but when we talk about correlation or coefficients, remember I was talking about the distance, the regressions. So I'm looking at the world from the scatterness. So generally, when people talk about correlation coefficients, they are talking about the scatterness world, and the scatterness world is based on EXEY, okay, not PXPY. And what's the difference between the two? Okay, the correlation, since this is about linear, so a lot of time that we're looking at the XY, okay, and well, imagine this, okay, I'm having a bunch of coins, a penny in my hand. I spread it on the floor. If my force, I learned Tai Chi or martial arts, so my force is very tight, very good control. You just see the coin spread in a strip, right? So you look at the scatterness on the table of those coins. Can you model them as a regression? You probably can. Can you calculate correlation coefficients? No problem, right? Yeah. So now you said X and Y are highly correlated, and X and Y probably are highly independent because they are from the same force. So if you see high correlations and say that Px and Py are highly correlated, therefore they are probably highly dependent. Correct. But let me give you a fun example. Remember, if x equal to r cosine theta, y equal to r sine theta, then I can build this whole thing like a big circle, right? So if I spread the coins, okay, for some magic, okay, they scatter like a big circle. Okay? It is still from my hand, still my magic force. So X and Y are really not dependent, right? It's all because of this force. But you look at that big splat on the floor and calculate the correlation coefficient. Are they correlated or not correlated? If it's a big circle, like a big pancake.
Not correlated.
So you follow me now? Correlation is afterthought. As you look at what's on the floor. And correlation is based on distance computation. Therefore, x minus x bar, y minus y bar divided by standard deviation. So correlation is very based on what's there. But this independency, px, py is the mechanism, that magic hand in my hand. Okay? And so stochastic process, okay, if you take 5302, it's based on evaluating what's there, what's in my hand. But evaluating what's afterthought, it's on the floor, that is what we're doing. And of course, I probably would rather study the hand, not study the scatterness on the floor. The thing is that in the real world, I already showed you guys, one, we can cheat, right? I can have adding a couple outlier to make correlation happen or not happen. So that's one. The other thing is that a lot of time correlation is very quick and dirty and get it done faster than figure out those probability statement. Probability is harder to study than in this. Okay, and now final thought. The other thing about correlation coefficients is, see here, once I have the beta, the parameter, can I build easy model to say that, go which way my parameter will be positive, which way parameter will be negative. So it can have a very nice cheat sheet done using correlation coefficient for the sense of directions. Okay? And if you go for grad school, I'll say both are important. Understand correlation coefficients, understand what's on the floor. Study the interactions or the source or the force, is study stochastic process. It's what is in Simon's hand before he done something. Is there any force related? Therefore, cause, effect can be evaluated and understand what's going on. And in grad school, it's called system identification. Okay? Okay. Everybody with me? Okay? Yeah. I'm still using the last 16 number, so you will have the answer in exercise. But once you understand how I'm looking at a world in 3 different ways, don't just stop there. You should ask, well, each view provides me something else. What is that something else? Okay? And yeah, I think I done all of them. Okay? And let's move to okay. Here is another things that people like to talk about is what we call R squared. How many of you ever heard R squared? Okay, R squared usually means whatever I can explain over the total sum of square. So what we did before, hey, I can explain, it's almost like a percentage. R squared is 0.85. 85.7% can be studied. Or, okay, of course, R squared should be the bigger, the better. But people think about it. Every time you use the R squared, just like I asked you guys talk about a lack of fit and pure error, the minute you start pulling something for your pure error or pull for your lack of fit, are they independent, or you take a little more lack of fit here, you're gonna less pure error there? You take something out from one side, you're going to lose the other side. So a lot of time, what we're trying to do here is called adjusted R-square. The adjusted R-square is saying that, okay, hey, explain this. Oh, I explained it. Oh, explain 60%. Explain this. Oh, I explained another 20%, now 80%. Hey, explain another one, another 10%. So sooner or later, I can explain. The more I explain, sooner or later it will be 100%, right? But is there a price you pay for that? Every time you explain that, you use some of the degrees of freedom from your error term. So here's the things. Let's just say exam is tomorrow, okay? And you only have, 10 hours or 8 hours to study. Would you study the most trivial stuff first, or you will study the most likely going to be in the exam first? Yeah, so in other words, is that when you're doing this adjusted sum of square, again, is that system engineering intelligence. Let me use the large one. Oh, the car got a lot of sum of square. Let me do the car first. Let me do the brand first. And so every time you do that, you said that, well, when I do the total degrees of freedom, how much I use for the car, how much I use for the brand. So I use 6 degrees of freedom. So every time I adjust that by the 6 degrees of freedom. And let me put a position in. Now I use 9 degrees of freedom. So every time you use the R square, if you just look at the pure R square, the more you put in, the more you're going to have. From 85.7% increase to 93%. Sounds good, right? But in reality, if I'm only using 2 car and brand, I explain the adjusted sum of square 76.2, and add the positions, it increased to 83.4. So if I'm running out of time, I will say that, hey, maybe I should stop here and not going too far to here. Okay? And one way I can also show you is this way. Okay? Say, here are the final grade of everybody. Of this many students. Okay? Pay special. Pay special. Value. No, Control C. Pay special. Value. And then data sort from the good to the bad. Okay? And then here are the total number of students, and here are their grade. Okay? And all I'm care about is that, okay, the school said that, well, this is this is pretty flat. People, if I said that I have to flunk few people, where is the flunk line? Where I put the flunk line, nobody can complain and said, well, it's based on the data. How many of you think that I should flunk anybody below 10? Student 10, 9, or if I want to have a flunk line, what would be a reasonable flunk line? 60%. Well, here are 22 students. Who can I flunk? And I probably can justify it. 1, 2, 3, 4, right? Can you see? Because 1, 2, 3, 4, after that, there's a big jump. Okay, and let's just say that I want to give somebody A. I probably can get it around 20. And then for B, I probably will get it around 12. Yeah, and the reason for that is there's a big jump. So if I flunk number 5, 5 will say that, hey, that's not fair. How come you didn't flung number 6? And so whenever you see there's a big jump, there is a partition point. So now, this is just trying to say that in the sum of square world is the same things. Who you say that, hey, I don't want to study this anymore, running out of time. It's basically said that which one doesn't give me the big jump. Okay? And that's the points I'm trying to make here. Okay.